different way to analyze a function today. Hey, understand that that's kind of what we do in math. When it comes down to it, we're either analyzing a function, by looking at maybe the graph of the function, or maybe we're analyzing it by looking at the equation. But if you think about it, that's what a lot of this year has been. We did it with sine and cosine. It seems like so long ago. And obviously in the present, we've been doing it with rational functions, which are like functions with asymptotes. But seriously, most of math is trying to analyze a function. And again, a function is either a graph or it's an equation. Now, what we're going to do today is we're going to analyze a function by trying to classify that. We're going to try to classify that D word. What is that sort of that D word? I'm purposely not pronouncing it. Do you know how to pronounce it? What are we going to classify? I'll just sort of say nicely, there's kind of a silly way to pronounce it. And sometimes our tongue sort of slips and says that. And then there's technically the right way to pronounce that big, long D word. It's very good. Did you hear how Hannah said it? Discontinuity, not discontinuity. It's a slight difference. It's a discontinuity. And I'm not going to grade you on the way you say it, but it's helpful to kind of have the right pronunciation. Now, what's a discontinuity? Well, the quick answer is it's actually what we've already been studying. Now, I told you we're going to study something new, but the truth is it's actually what we've been studying with a couple new sort of twists to it. The reason that it's a little bit of what we've already been studying is because technically a discontinuity is a place. A discontinuity is a place. It's a place where a function is undefined. A discontinuity is a place, as it says there, an x value where a function is undefined. Now, I know that you're writing it down. That's a good idea. You probably should write it down. But just stop for a moment, or at least think with me for a moment. What do I mean by undefined? Okay, we're kind of getting into some of the theory of mathematics. Undefined means that it has no value. And there's one special fraction that has no value. It's actually what most of this chapter has been built upon. It's that darn zero in the denominator. You can't give chocolate to 0 students. Okay? You can't divide by 0. So what I'm saying is that a place, one of those places is going to be if you have a 0 in the denominator. I know, I'm sorry, it's actually somewhat of the same thing that we've been talking about. That's why it fits into this unit. Okay? Well, more on that in a moment. This is the part that people kind of like. It's kind of the new part. This idea of a break in a graph, a break in a y value. A discontinuity is a place where if you're drawing a graph, you'd have to pick up your pencil to continue drawing the graph. A discontinuity is a break in a y value. And that leads us to this kind of, well, sort of fancy schmancy graph. Now, we're going to do a bunch with this graph, so I will actually pause here because a lot of kids like to jot this down. Again, you're probably jotting a couple things down, but unless you have photographic memory, you're going to probably want to have this in your notes, okay? Because we're going to do some things with it. As you jot down this graph, maybe notice places where it seems like there's a break in the graph. Notice some of the places where it seems like it's undefined. Or just sketch it. Just sketch it because we're going to talk about it anyway. I noticed my finger kind of smeared this, but this would be filled in right here at x equals 2. That is filled in. All right, now I told you that there was something kind of new and fresh today, and it honestly is how we're going to look at this graph. Would you pretend with me for a moment, maybe bring out your inner child and do a little pretending that we're just going to take a walk along this graph. Now, this is not like a walk for the faint at heart. This isn't just a nice little stroll in the park. Okay, this is going to be quite a walk. But in math, we always walk left to right. So we're going to start right here. Okay, so maybe grab your special other and we're going to start taking a walk. And I'm being honest here. Where are we going? Where are we going as we walk down, down, down? Or where are we coming from as I come from up, up, up? Where am I going as I start my journey? I'm going to, or I'm coming from, well, infinity. Do you agree? As I walk close to this vertical asymptote, which I can't touch, but as I walk close to it, I find myself walking to negative infinity or coming from positive infinity. Why am I making a big deal out of that? Well, because your first discontinuity is an infinite discontinuity. An infinite discontinuity because literally I'm going to infinity or I'm coming from infinity. Now, look at a little bit of the notation here. First of all, we have a new word. Well, you've heard the word infinite, but we use that word to describe a vertical asymptote. An infinite discontinuity is really a vertical asymptote. But it's because we literally are going to infinity. And as you're going to find out today, discontinuities, the way that we describe them, have to do with what is happening on the graph. Now, there's another little detail just in the first problem, but you're going to see it for every problem after this. You always give the location of a discontinuity by giving the x value. So if you say, where are you, Mr. Naylor, on your little journey? You would give the x value. So notice that we say at x equals -3. Okay, but sometimes kids summarize this and they'll quickly say, well, that's just a vertical asymptote at -3. Yep. Okay, you're right. We're just calling it infinite discontinuity. Okay, now it was a long walk because you walked to infinity and somehow you're coming from infinity. So I know you're tired, but let's keep walking. And so we come to this spot. Now, when you come to this spot, you kind of like, whoa, how am I going to get from here to here? If I'm standing here, how am I going to get here? Well, you literally would have to jump. You literally would have to jump, except I'm jumping down. I literally jump at that x value. Guess what the next discontinuity is called? You're right, jump discontinuity. Now, I'm not making this up. It is a mathematical term. By the way, if you keep taking more math, which would be calculus, you will continue to talk about a jump discontinuity. So what do you think? Jump discontinuity. Notice what is true, that you start and stop at a different y value. Again, you start and stop at two different y values. It just kind of a little, by the way, this is one of the nice things about this lesson. Like so far, the stuff that we're showing you, I don't want to call it common sense, not common sense, but if you just think about what it's saying, it literally is describing the behavior on the graph. So it's kind of nice that what is written up here is exactly what you see. But I want you to notice something about the way I'm giving the address. And this is kind of one of those things that kids sometimes have trouble with. Sometimes when kids give the address, they feel like that they are at two places. But I don't want you to feel that way. If you're going to address the jump, if you're going to say, hey, go to the jump, and somebody says, where do I go? I know I'm pointing at two places. Well, actually, I'm pointing at two y values, but that's one x value. Okay, now, maybe it's not real hard for you, but I just want you to realize that when you look here, don't see two x values. You only see x equals 2. Okay? Now, if you see something that's 2, you're seeing two y values. But the address is always the x value. Okay? So again, this place, even though I'm pointing at two y values, this place is x equals 2. All right? So you kind of pick yourself up, dust yourself off after the jump, and we're going to keep walking. We're going to keep walking. And we're not watching our step, and suddenly we fall into a hole. We fall into a hole. We give it a new name, because really a hole in the graph is a point that's missing. It's a point that's missing. We call it point discontinuity. Now, I did say it's a hole in the graph. You know, like a hole in the graph from the last week, but it's just a point that's missing. It's a point discontinuity. It's actually a y value that's missing. And that's why you're going to start and stop at the same y value. I know it's written up here. I know you can see it, but I just want to highlight it. The address, the place, is just the x value. Now, if you're thinking, you would realize that just yesterday we were trying to give the point as an x and a y value, like 4 and -2. But when you technically talk the talk, you just give the x value for the location. So you would say there's a point discontinuity at x equals 4. You do not have to give the y value. You actually don't want to. Okay, now you pull yourself up out of that hole, friend pulled you up, and you're ready to keep walking. Now, as you walk, I got a question for you. Did you pick up your pencil yet? How about now? Did you pick it up now? Did you pick your pen? How about if I walk along this graph, is there a place where there's a break? Is there a place where I have to pick up my pencil? Even though I'm getting closer and closer to this horizontal asymptote, it's not a break in the graph. It's not an undefined value. I don't have this up on the screen, but you might want to just mention it either on your graph or in your notes. A horizontal asymptote is not a discontinuity. Did you hear that? A horizontal asymptote is not a discontinuity. It's not a break in the graph. It just is a boundary. Another way to say it is it's not an x value. This is kind of the technical piece for my technical kids. This horizontal asymptote is not an x value, and therefore it's not a bad x value. Okay? It happens to be a y value. That's why it's not a discontinuity. Now, there's one more discontinuity that's going to fit in this spot. I'm telling you that because you might want to skip a little space so that when we come back to it, maybe you feel like everything's kind of organized. But I am going to move to the next thing, which is actually the same thing that we just did. We're going to classify and locate the discontinuity. Now you say, Ms. Naylor, what do you mean it's the same thing we just did? Well, we're going to classify and locate discontinuities, but now we're going to do it for equations. Like I said, skip a little space because there's actually one more classification, but I want to show it to you through this part of the lesson. Okay, now kind of a little warning. This is the part of the lesson where if you don't kind of stay engaged with me, you might make it too hard. Don't make it too hard. But yeah, now I gave you an equation. And obviously equations are a little harder than just looking at a fun graph. You can still do this though. Again, warning, don't make this too hard. Now, one thing you're going to realize is that we're still giving like two answers. We're giving a classification and a location. I'm going to try to denote that with sort of two blank spaces. You decide if you want to do that. I just want you to know we kind of need to give two answers. Are you ready to find the location? We're actually going to find the location first. Now, I said it at the beginning of the lesson, but here's where you realize what I kind of meant. A discontinuity is an undefined number. You know, a bad number, like we were kind of saying the last few weeks. Bad numbers happen when you have a zero in the denominator. Now, if you look at this statement I wrote up here, it can be solved for x. One way you can solve it for x is by adding 4 to the other side and taking the square root of both sides. It's kind of like just solving for x. Now, you end up with a plus or minus. You end up with a plus or minus, which is important, and of course the number 2. Guess what? That's the location. That's the location of our discontinuity. Plus or minus 2. Some people feel like I'm doing this backwards, but I'm actually trying to show you that we can find the location with just simple bad numbers, you know, like a 0 in the denominator. Okay, now here's the part where you kind of have to use, I'll say, a little bit of a mixture of knowledge. And that mixture of knowledge would be that since we've studied this for the last week or so, that you would say, boy, geez, what is going to happen at plus or minus 2 when I have a fraction like this? Basically, what is going to show up on the graph? And from the last week or so of knowledge, you would conclude that it would have to be a vertical asymptote. Now, your pause or your silence is not uncommon because kids are like, I don't know, what is going to happen? Well, again, a vertical asymptote. You've seen it over and over. There's going to be a vertical asymptote when you have a 0 in the denominator. Now, don't write vertical asymptote. That sounds kind of sounds old. We have this new idea. It's really just a new word. We call it infinite discontinuity. So yes, I want you to write the word infinite. Okay, so we used a little bit of old knowledge. We also found the bad number so we could classify and locate. Those are absolute value symbols. Absolute value of 3x divided by x. The absolute value of 3x divided by x. Now, maybe you're saying, this looks kind of new. Like, I don't think I saw this one yesterday. No, you didn't. But before you get worked up about what's new, I want you to think about what you already know about the denominator. Look, I'm trying to give you like a strategy, and the strategy is find the bad number. I'm telling you, the bad number, which by the way is 0, is going to be the location. The location is always the undefined number. Now, you would want to pause and say, wait a minute, I haven't seen this before. I haven't seen absolute value. Is it a vertical asymptote? Again, I'm saying that that's the kind of thinking that should go on in your head, which would mean that you would want to further investigate the graph. So we're going to appeal to a graph. We're going to appeal to Desmos. The absolute value symbols actually are on your keyboard. It would be in the right-hand side of your keyboard if you're using a computer, or you can find the absolute value symbols on your phone. Now, this is not a graph that you saw yesterday or the day before that. Okay, it's different. In fact, if I was going to walk along this graph and my name was Mario and maybe my friend's name was Luigi and I'm kind of walking along that graph, what's going to happen when I get to x equals 0 so I can continue searching for coins? Mario's going to have to, he's going to have to jump, right? Literally, you have to jump to continue your journey. I didn't want to jump up to the higher platform and fall on my face. Where's the jump happening? Listen, when kids look at this incorrectly, they say -3. The jump is not happening at -3. The jump is happening at x equals 0. Where's the jump happening here? It's the same answer, x equals 0. Don't say 3. Okay, so you would say, hey, I'm going to jump at x equals 0. I'm going to jump at x equals 0. This is a different kind of graph. If you're like, whoa, I didn't know that. That's fine. It's new. That's what happens with absolute value. Let me say that again. That's what happens with absolute value. But you can graph it. Like next time you see this, pull out Desmos and see what it looks like. You're going to see a jump. I don't mean this as just something to say, but do you have any questions? Is there something that has popped up that I don't want to gloss over what was new here? Okay, well, here, let's look at another equation. F of x equals x squared minus 1 over x plus 1. F of x equals x squared minus 1 over x plus 1. Now, at this point in the lesson, sometimes kids are like, I thought I was catching on, but then you did something different. Well, I want you to catch on, and I want you to realize that I am not doing something different every time I locate. Okay, I'm serious. I'm walking along. I got my metal. Saw a guy with a metal detector yesterday, like in the middle of like a farm field. I was kind of wondering like what might have been spilled there. But we're walking along, and we're looking for the discontinuity. We're looking for the location of the discontinuity. Are you catching on that it's always the undefined number? Okay, now I hope you're not waiting for me to say x equals -1. Okay, and x equals -1. That idea hasn't really changed since the beginning. Look at the numerator. Now, this is one of those things where trying to get you to sort of be that math mind. You're in a higher level math class, so you look at x squared minus 1, you say, what am I supposed to say? You're supposed to say factor. It's just kind of one of those things. Do you realize that it can be factored? Now, if you didn't, then kind of put that on the radar screen. Because anytime you can factor something, you should. I say anytime. I mean, honestly, probably just about at any time. Because it helps you to see things. To see things like... Now, of course, that should catch your attention because that's called a common factor. We have a common factor in the numerator and denominator. Wait a minute, that's something that we're supposed to know about. What happens when you have a common factor? What happens when there's a common factor? It creates a whole. Now, that's very good because that's exactly what you've learned the last few weeks. It's just that today we have a new name for that. I'm sort of erasing my lines here, but we have a new name where you would say point, discontinuity. Again, Thomas is completely right. It creates a whole. That's what I want you to say. But now we call it a point discontinuity. We've used a mixture of methods. You have to understand that this problem, we kind of just used some general knowledge and said, hey, that's a vertical asymptote. It has been yesterday, it will be tomorrow. This is new, so we graphed it because maybe we weren't sure. This one, we see a special common factor. It's a mixture of methods. Okay, you have to be okay with using the correct tool for the situation. And now we come to this fraction. Are you still engaged with me here? Okay, now soon you're going to do these on your own. I hope that you're going to try to use kind of my style here, my technique, which is to think about the denominator. Wait a minute. What number, if you square it and add 1, what number, if you square it and add 1, is going to equal 0? A positive number? I don't think so. A negative number? Well, what happens when you square a negative number? It's just going to be positive anyway. Wait a minute, hold on a second here. What number, if you square it and add 1, is going to equal 0? No number. No number. Now, that means that there's no discontinuity. Let me say it again. There's no discontinuity, which means, and this is our 4th classification, which means the graph is continuous. Check this out. I don't want you to make this too hard. It's actually no discontinuity. We say it's continuous. Now, did you leave some space to put that in as your 4th classification? There's no break in the graph. There's nothing undefined. There's no break. There's nothing undefined. Continuous would be the answer. But I want you to understand it's because there's no bad number. Continuous would be the answer, but it's because there's no bad number. By the way, You don't give the address if something's continuous, because continuous means everywhere. So we don't have to say where. It's assumed that it's implied that it's everywhere. I know that I might be the only one with Desmos out. I see a couple of you with it on your phone, which is fine. I just want you to realize that you are allowed to graph these. You know, you get to a problem and you're kind of like, I don't know, I'm not sure. Okay, you can graph it. This is kind of an interesting graph. It doesn't have any asymptotes. It actually just kind of, you go up the hill and you go back down the other side. But yeah, there's no place on that graph where you fall in a hole. There's no jump. And you don't go to infinity. Okay, that's because it's continuous. Now, I got one more problem. I hope that you will stay engaged with me for just one more problem. It's kind of in the same theme. We're trying to classify and locate basically the type and the place. Okay, but you wouldn't be the first student if you're like, whoa, wait a minute. Now you just, you change things up on me. Well, I'm trying to hopefully make you realize, no, I didn't change things up. It's just that it's a piecewise function. Okay, now piecewise functions, they don't necessarily have a denominator, so I can't think about a zero in the denominator. But piecewise functions, they do have behavior. They're basically a graph, kind of like what we started with. This was honestly a piecewise function. I just didn't give you the equation. So guess what we have to do? It's not necessarily everybody's favorite thing to do, but we have to try to graph this piecewise function. Now, this is something we did back around winter, and I know you studied it other places, but we want to try to say, okay, if I had to graph x squared plus 1, now, if you just stop right there, x squared plus 1, maybe you type that in a Desmos. Maybe you think, wait a minute, that's just a parabola. That's a parabola that shifted up 1. I'm not going to give you the hardest piecewise functions, so I think we can come to the conclusion that we have a parabola that shifted up 1. Now, it's not the whole parabola because it's only the part less than 0. Remember, less than 0 means to the left of 0. So eventually we want to say only this branch, only this side. I'll get rid of the dotted lines over here, and I'm going to open this up because, of course, it's not equal to. Now, I said if you needed to use Desmos, you could, but I'm trying to encourage you to think about what you've learned about x squared plus 1. X. I find that sometimes kids have trouble with x because it's so simple. It's like y equals x. Oh, y equals x is like a diagonal line that has a slope. A diagonal line that has a slope. So yeah, you know how to graph that. Carefully, right? You want to carefully graph the part greater than 0. Now, greater than 0 is going to be the part that goes to the right of 0. Listen, really the answer for this problem is a careful graph. Because now I hope that everyone would say, yeah, if I'm going to walk along this graph, this is just one of those examples that Ms. Neller said you're going to have to jump. You're going to have to jump. Now here's where I would love to see you get this right. The location of the jump is not y equals 1. It's not y equals 0. The location of the jump is the x value. The x value, whether you're here or here, is x equals 0. X equals 0. One more quick thing before you pack up. You can just listen to it. Somebody says, Miss Neller, that's a hole in the graph. I say, no, it's not. Why? Why is it not a hole in the graph? Don't say because it's a jump. Tom? Okay, that's spot on. But just everybody process that with me. There's two. It goes from one to the other. Okay? Again, I know it seems like they're both open circles, but it's two different values. So it's a jump at x equals 0. I hope you found discontinuities to be somewhat refreshing. Maybe you can pronounce it a little better. Take a look at the homework helper. Okay, pretty common little homework helper. Keep up the good work.